Let's look at part C here. You might think, okay, can I separate these? What can I do? And the answer is no, you can't separate them because there's two terms in the bottom. That's not the trick. But what we do know is the highest power on the bottom is x squared. The highest power on top is an x. They differ by 1 power, so that's a nice trigger to know. Possibly use substitution on this problem. So it's the integral of x plus 1 all over x squared plus 2x with respect to x. Step 1 would be let u equal the higher of the powers, so that would be the x squared plus 2x. And then step 2 is find the derivative of both sides. So if I found the derivative, I'd have du dx equals, well, the derivative of x squared plus 2x would be 2x plus 2. And I just want to notice that that's equal to 2 times x plus 1. Okay? I could factor out the 2 is all I did there. Okay, step 3, again, solve for dx. And I'm going to note that dx equals du over 2 times the quantity x plus 1. That's just multiplying both sides by dx, dividing both sides by 2 times the quantity x plus 1. Why did I do that? Because I had the foresight of looking ahead of what u was and what du was and what was going to simplify. So I saw that I needed the x plus 1 to simplify. That's why I factored out the 2. It's just a little foresight in seeing in the original integral what am I going to need to simplify. So let's go ahead and replace in u, and we need to replace in for u, and we need to replace in for dx in the original integral and rewrite it. So step 4, I would have the integral of, on top I still have the x plus 1, on bottom instead of x squared plus 2x, that's u, and then instead of dx I had du over 2 times x plus 1, the quantity x plus 1. So when I simplify that, the x plus 1 simplify, I realize that the 2 is just a constant multiple. It's actually a constant multiple of 1/2, so be careful. So this is 1/2 times the integral of 1 over u du. Now step 5, now that it's all in terms of u, I can integrate it. So this would turn into 1/2 times the natural log of the absolute value of u plus c. Okay, nothing to simplify there. The only thing to do is to substitute in for u. So step 6 would be 1/2 times the natural log. Instead of u, I'd have x squared plus 2x, and then that's plus c. My final answer right there, 1/2 times the natural log of the absolute value of x squared plus 2x plus c. Nice little problem for you. Okay, let's go on to d, which is the integral of 1 over 3x plus 2 with respect to x. Again, here a nice u substitution problem. Let's let u be the denominator, so let u equal 3x plus 2. Step 2, find the derivative of both sides, so I'd have du dx equals the derivative of 3x plus 2 is simply 3. Step 3, solve for dx, so dx would equal du over 3. Think about replacing back into the original integral. We need to replace in dx, and we also need to replace in u. So when I rewrite this integral, this would turn into, this is step 4. This would turn into the integral of 1 over, instead of 3x plus 2, that's u. Instead of dx, I have du over 3. I notice that my constant multiple here is 1/3, so I pull that out. So now I have 1/3 times the integral of 1 over u du. That's easy enough to simplify, to integrate, so that's 1/3 times the natural log of the absolute value of u plus c. Last step to do, since there's no simplification, is back substitute for u. So I would end up with step 6. I would have 1/3 times the natural log of the absolute value of u was 3x plus 2 plus c. And that's my final answer right there. 1/3 times the natural log of the absolute value of 3x plus 2 plus c. Okay. So, what do we have on this next one right here? On this next one, we're going to have to remember an algebraic technique. This is something that you probably learned in intermediate algebra, certainly learned it in college algebra if you took those courses more recently. This one's not as easy, and let me tell you why immediately I know it's not as easy. I'm looking at the integral of x squared plus x plus 1 all over x squared plus 1. if you notice, the degree on the top is the same as the degree on the bottom. In all the previous problems, you had it off by 1. So for instance, if it was x to the 4th on bottom, it would be an x cubed on top, right? I don't care about the coefficients. You can deal with the coefficients later, but you have to have the power a difference by 1. So on this one, I know U substitution would not work because the degree of the top is the same as the degree of the denominator. So what do you do when the degree, when it's balanced? Let me just go ahead and write this down. Difficult because it's balanced. And again, what do I mean by balanced? Balanced, I mean the degree on the top is the same as the degree on bottom. So what do we have to do? We actually have to do long division. Long division is side math to see what this would actually equal. So we have to see how many times would x squared plus 1 go into x squared plus x plus 1. Well, the idea is, how do I make the first term look like the first term? Simply multiply it times a 1. If I multiply it times 1, 1 times x squared plus 1 is x squared plus 1. I do my subtraction between the two. X squared minus x squared, 0. X minus 0 would be x, and 1 minus 1 would be 0. So now the question is what do I do to get x squared plus 1 into x? And the answer is I can't do anything. So this right here is my remainder. So what is x squared plus x plus 1 divided by x squared plus 1? That means x squared plus x plus 1 all over x squared plus 1 is equal to what we got, which was a 1, plus the remainder, which was an x, over divisor, which was x squared plus 1. Okay, so remember, this is what goes on top here is your remainder, what goes on bottom here is your divisor. So it's your quotient, which was 1, plus the remainder over the divisor. That's how long division worked. So what's the idea then is, instead of integrating this one, you're going to integrate what we just got right here, the long division, which was the quotient, 1, plus the remainder, which was x, over the divisor, which was x squared plus 1. Now all of this is with respect to x. Now this is something that is a lot simpler to integrate. We could break this into two separate integrals. We have the integral of 1 dx, which is very simple. That's just equal to x, right? Plus c, but it's equal to x. Plus, now we have the integral of x over x squared plus 1. Notice now that the degree on bottom is 1 higher than the degree on top, so this tells me I can use my u substitution, right? So step 1 would be let u equal the bottom, which is x squared plus 1. Step 2 would be find the derivative of both sides, so du dx, the derivative of x squared plus 1 is simply 2x. Step 3 is solve for dx, so dx would equal du over 2x. Step 4 would be rewrite that integral. So this would be the integral of, well, it would be x over u times, sorry, there needs to be a dx there, times du over 2x. Notice the x's simplify, so this is equal to, pull out the constant multiple of 1/2, the integral 1/2 times the integral of 1 over u du. Step 5 would be integrate that, so that would be 1/2 times the natural log of the absolute value of u plus c. Now we know we need to back substitute for that u. Sorry, let me highlight my dx's and my u's. So I need to back substitute for that u, and when I back substitute for that u, that would give me 1/2 times the natural log of the absolute value of x squared plus 1 plus c. So that's just that second integral. I still have the first integral, right? So this is equal to x plus 1/2 the natural log of the absolute value of x squared plus 1 plus c. So looking at this, this is the same thing as they have in the book, except they do one thing different. What they realize is that x squared plus 1 always has to be positive. x squared plus 1 is always positive. And because it's always positive, technically, if you simplified it, you don't need those absolute values. So in the book, they use parentheses instead of the absolute values, noting that x squared plus 1 is always positive. Quite honestly, I don't care if you noticed that or not. I'm happy that you got the answer as is, that you knew to use long division on this problem. So I'm going to give you full credit whether you have that absolute value in that problem or if you actually did realize it's positive and not have the absolute value in the problem. So anytime it's difficult, anytime it's balanced, you must use long division. I promise on the test, if it does happen, that it's not going to be a crazy long division. It's not going to be 14 steps of long division to figure this out. It'll only be 1 or 2 steps to figure it out, just like it was in this problem. So again, we knew this problem was a little more difficult because it was balanced. We tackled it by using long division.